All right, we'll get started. So thank you everyone for joining, and welcome to today's SPE's Engineering Properties and Structures Division webinar. My name is Sean Teller, and I'll be your host for the session. And as we begin, I just want to make a few quick announcements and housekeeping announcements. So first, all attendees will remain muted during the presentation, but you can submit questions at any time using the chat function, and I'll be corralling those for Dr. Wang. We will collect questions throughout and address as many of those during the Q&A as possible at the end. And the webinar is being recorded, and actually at the you should receive a recording once that's complete, probably next week. It's my pleasure to introduce today's speaker, Dr. Xiqing Wang from the University of Akron. Dr. Wang received his PhD in physics from the University of Chicago, held faculty positions at Case Western Reserve and the University of Akron. He's currently a distinguished professor at the University of Akron and has made significant contributions to the fields of polymer rheology, ductility, fracture, and adhesion. He's also the author of the book Nonlinear Polymer Rheology and has a second book, Polymer Physics, Ductility, Fracture, and Adhesion, being published this year. Today's presentation is titled Ductility and Brittle Fracture in Plastics, Building Processing Structure Property Relationships. On this webinar, Dr. Wang will discuss how processing influences polymer structure, how structure influences mechanical properties, and ultimately how plastics become ductile or brittle and fail through fracture. The presentation will cover topics ranging from polymer rheology and processing to ductility, brittle to ductile transitions, and fracture mechanics. With that, Dr. Wang, thank you for joining us, and the floor is yours.
Okay, thank you. Thank you for having me here. Time is short, so I will just give you some brief review of what we have learned over the past 20 years. And the goal is to give you some information so you can use AI to learn more about it. Speaking of AI, if you ask any of these topics, AI will mention nothing about what we have done. So I'm actually proud of the idea that they cannot find what we have done, because that's mainstream ideas. And what we found is a lot of new information and understanding, very much opposite of what the prevailing understanding is. So use your AI, but now you prompt it with my name in it. It will tell you the relationship between what we do versus what the rest have done, really. And we have, of course, been standing on the shoulders of previous giants, so we could see a lot further. And I'm proud to be able to show you what we learned with questions such as what structure is good for us, polymer-wise, and how to achieve such structures, and deal with the issue of ductility and fracture. So the holy grail is processing structural property relationship, and how do we establish it? So this is a picture with the three generations of students. First generation working on rheology, second generation working on ductility, and the current generation, many have graduated already on fracture. And we were fortunate to be able to do this because of the continued support from National Science Foundation, and Andy Lavinger just retired recently. And we are indebted to him because of his belief in what we do, what we have done, and supported us. So I will start in a rather unconventional way. I will just try to review for you what we already know. Whether we understood it, that's the question, right? So we already know that there's such a thing as Mylar. If you check the list, it's one of the most wonderful and industrial inventions. And you know what it's based on? It's based on PET, actually. It's a biaxial-oriented PET. Why it has such properties? Well, if you finish this talk, listening to me, probably you would know why. So secondly, we are able to show that through a similar piece of physics, the nasty, brittle PLA can be made to be ductile, and we have made one of the first transparent, heat-resistant, and super tough PLA cup as shown in this movie. This sample is strong even at 100 degrees. So this is something that we have previously established. It is also known that the most ductile polymer, such as polyethylene, can be brittle if you have too much crystallization. Why? Well, that's something we think we understood very well now. And PP, polypropylene, is growing in market share, but it is not one of the most fast crystallizing material. So depending on how you control the crystallization, you can get huge morphology differences, and that affects ductility. And when it's brittle, because TG is only -10, when it's below TG, it tends to be brittle. And people using the biaxial stretching to solve that problem. So lastly, it is known that even ductile polymers can be brittle in presence of a so-called notch or crack when the sample is thick enough. So this is just a movie showing, now we know how to show it, that even a ductile, very ductile polymer like polycarbonate, bisphenol A polycarbonate, turns brittle. So clearly what we need to know is to figure out the relationship. And I want to say that the relationship between structure property is usually you know the property, you want to know the structure. And that's an inverse problem, infinitely hard to solve because many structures can produce what you see. But which structure do you see? And if you don't know that, you cannot use processing to design and achieve the structure you like. And to understand processing, you have to know the basic rheological principles. So that's the chain we're trying to build up. So over the last 25 years, we are trying to build this chain. So go through the different pieces of this puzzle, learn about rheology, learn about ductility, and start to learn about fracture. And the knowledge is in this two book. AI doesn't know it. I'm sorry to tell you, and I'm proud to tell you they don't know it. I'm being sarcastic here, heavily. So in any case, I'm not going to say a great deal about fracture, except near the end. But if I missed anything, you can find it in my channel, YouTube channel. You can find it in the upcoming book. Half of the book is about fracture, because that's the part that it was heavily misunderstood about polymer fracture. So I intend to show you this chain of processing and rheology and all that. So let me very quickly say that rheology can be a nasty problem in processing of polyethylene. For example, you have this kind of melt fracture, so-called. And that was the inspiration for us to look into rheology and understand the origin of such things. So it has to do with whether there is wall slip, and this is just some of the illustrations of that type of feature. At the end of the day, we find that we cannot treat our polymer molten polymers in processing as a piece of fluid, but rather they behave solid-like. So we need to understand their startup or transient behavior. And this is one of the movie by now. It's close to 20 years old, showing that this innocent flow-like behavior is not so innocent. You see, it breaks as if it was a piece of solid. So it's uneven deformation. And this uneven deformation carries all the way through during processing. So for example, this movie was showing extrusion, but when you try to extrude very fast, at the end, you find your extrudate is distorted. And we know exactly how this occurs by looking at what happens as the polymer rush to converge into the die at the entry. They suffer this solid-like failure. So this is, again, it's all published. It's in book 1. But it's very telling. It tells you should quit doing your finite element calculations if you are still based on constitutive models, because this is is a internal structural rearrangement that is not captured in constitutive model. So in any case, we can even build a basic conceptual level understanding of it. I'm going to skip how I illustrate this, but this is all discussing the text in my book. And my YouTube channel also has a recorded full course based on this book. So speaking about what we learn in rheology, I listed a few parts about where our knowledge is relevant, guiding our processing. And I'm not going to spend time. I'm making the slide so that's recorded. We can come back to it, ask questions. But let me move on to the solid state, which we hope to use rheology to influence in terms of structures. But what structure you have? Well, the structure you have from rheology, we know it's like a ball of spaghetti, and we can characterize how long the chains are, can affect the viscosity of it, the solid behavior, the degree of so-called entanglement can be defined in different ways. To us, it seems important the entanglement is arising from this uncrossability, which is preserved when you go to the glassy state. It's still there, that entangle, that uncrossability. So through rheology, we learned also about the solid structure, which is a matter of acknowledging that there is this underlying polymer network. And the structure can be universally described. I'm skipping the more details, but come to the question of what it is, the question to ask, then there's a question of how come your glassy polymer can be ductile? That's essential, meaning your polymer is ductile, is probably the most profound property or the reason we're using polymers. The brittle polymers can be used, but only for certain applications. So we need to understand how to make a polymer ductile, and when does it become brittle, and eventually learn about a new perspective on fracture mechanics. So briefly, ductility is about drawing a piece of material. You have brittle behavior. If it's blue, it breaks when its force is still growing, or it can undergo so-called yield. This movie was showing you it was undergoing 45-degree shear yielding, and then next, and that's the desirable features. But really, how do you understand that fact they can yield? And I list 4 ideas here. None of them, in my opinion, really satisfies what I think should be understood about the nature of this ductility. So I will briefly go through each one of them. There is this hypothesis that you can learn about it. They basically says lower stress is the winner, and the higher temperature yield stress is lower. And the yielding, of course, is explained based on this iron. I see missing a D here. Iron idea, and it's generally regarded as the simple way to understand where ductility comes from. But it doesn't tell you in this theory where the stress comes from. So then there is this continuum approach of Eilhoven's group, which was really treating this brittle failure as an extreme form of strand localization, and they tried to do it at continuum level, mathematically showing that the features of the strand hardening, softening could influence the outcome or the degree of strand localization. Again, it's a continuum level. It doesn't go into the details of what happened to the molecules. And there's a more molecular approach, try to correlate secondary relaxation with brittle ductile transition, but this correlation is not causality. So coming back to why polymer is ductile, is why the monomers can become activated. So that process in determines whether ductility occurs or not. So this is just some old data showing that if you have polystyrene or PMMA, high temperature is ductile. As you go through this cooling, it turns brittle. So for example, at 50 degrees, PMA is about to change from brittle to ductile. And this old paper discovered that if you pressurize your polymer can turn from brittle to ductile at room temperature. So this was an interesting finding. But generally, I can summarize that there are many factors to influence brittle duct transition. I just showed you pressurization can change it. And these three factors is changing the way packing occurs. And these two factors I'm going to review for you is changing how chain network is changed. So one of the most amazing one is this so-called mechanical rejuvenation. And this movie from Eindhoven shows how it happens. This brittle polystyrene, after going through a two-row mill, is brittle. Turns ductile. So beyond that, we know when even the ductile polycarbonate upon aging turns brittle. So that's the aging. So you can see these are three factors that influence brittle duct transition. And then it's known for now 60 years that your polystyrene, which is brittle, can be made ductile if you pre-melt stretch it. Okay, so what I learned that is it has produced a different structure through geometrical condensation. So all the network is collapsed, become more into the transverse direction and become more effective in causing activation. So, and then if you do it, draw it perpendicular to the pre-melt stretching, even ductile polymer can turn brittle. I know I'm being brief, but it's all published, so you can find any of this. I want to emphasize one thing, that the molecular weight, the reason we have to have high molecular weight is without high molecular weight, the sample is very fragile. So one of the things to entertain you is to show you that polystyrene that is very brittle, as you can see from the bending, is totally ductile in compression. Okay, so I think we understand it among the first why this occurs. It has to do with this pressurization causing polymer to turn ductile. But molecular weight is still important. So if you have a molecular weight that's only 50,000 K for polystyrene, look, even compression gives you brittle response. So in any case, I'm going to only very quickly showing you how we tackled this, how we understood this change from brittle to ductile, taking into account all the 5 factors that influence this brittle ductile transition. At the end of the day, we acknowledge when you have high molecular weight, the chains have the chance to hook onto each other and form junctions as part of the network. And this unit repeats itself millions of times when you have a microscopic sample. And you are just holding two ends of the sample, try to stretch. As you do, this network, of course, will also try to undergo displacement. So it's moving along, trying to drag along the dormant segment that's in there. And the question is really whether you are successful in wakening up this dormant segment to participate in the shape change. See, when you elongate, what happens is if volume is conserved, if you elongate, the transferred cross-section must proportionally contract, shrink. And that requires the whole sample to have enough mobility. So about 12 years ago now, I visualized that the role of the chain network is to encourage mobilization and through this load-bearing strands. And this is described in heavy detail in chapter 6 of the upcoming book. So if I'm being brief, you'll soon see the book. And I even have lectures in my YouTube channel about this model. So in some detail, basically, it is very logically concluded that the brittle ductile transition is sitting at the Goldilocks temperature, below which the network failed to bring about enough mobility, and it will break down. And above that temperature, the network is robust and intact, can bring about a sufficient mobility. And this breakdown is understood in this language as the chain pull out. So the blue chain, when you displace your polymer, if temperature is too low, cannot remain hooked with the red chain. They will start to pull out. So with this, we have the benefit of this picture showing us how to think about the origin of stress as it relates to the structure of the polymer. So there is a particular theoretical result that's coming out of this physical picture. So with that picture, we now design or overcome the ductility of famous brittle polylactic acid. It's a paper, it's a polymer, thousands paper written on it because it's supposedly sustainable. But it's known to be brittle, but we know through processing, as we showed in the case of polystyrene, if you can melt process it, your polystyrene turns ductile because of this geometrical condensation. In fact, you can achieve that geometric condensation in both directions. So to do so-called biaxial stretching. What was visualized at that time was that I realized that you can do this stretching in the melt state. And when the chains lined up, you also encourage crystallization. PET, PLA, they all can crystallize, but generally crystallize very slowly. But with enough of orientation, of local chain orientation, they can crystallize. And I envision that this crystallization will occur within each mesh size of the network. So the crystallization will necessarily be nanoscopic, and therefore making your product transparent. So this was the idea. It turns out this idea that's guided by our understanding of why ductility can be achieved is the same idea that explains why Mylar works. So Mylar was invented in the 50s. I don't think they have the theory at the time. It just magically worked. Now you know why. So your Mylar is transparent, but it's heat resistant because you have crystallization that doesn't melt away until 250 C. So this is my best example of showing brittle ductile, of showing the so-called PSP, processing structure property relationship. We know the structure need to be such that it can deliver ductility by intensifying the network strength in this XY direction at the sacrifice of the third direction, which is the film direction. We don't care. And then that is achieved through rheology. And once you have that, you can encourage the structure that involves crystallization. So you have the double benefit of achieving crystallization without sacrificing the transparency, and also achieve ductility. So this is really, I'm proud of this way of guided by theoretical understanding to invent a material, if you like, or predict the property of the material in this case. Again, this is discussed in the book. Chapter 7 was on ductility or drawability of semi-crystalline polymers. Chapter 6 was on glassy polymers, meaning amorphous plastics. So again, if you check with your AI, I think my theory is nowhere to be found. If you just ask, hey, what is the understanding on brittle ductile transition? Work at Akron probably does not appear in your search. I sarcastically say I'm proud of that. That really is a disaster that shows you are being misinformed. It will describe the 4 things that I described to you. Let's say I have time, so it will describe this 4. It will describe all this 4 except my theory. Wonderful. I'm not upset. I'm actually happy, as I told you. So, let's do this, folks. We're working on polymers. It's exceedingly complicated. Nobody has any proper theory to handle it. That's why in rheology, I wrote this book here, because we oversimplify the rheological behavior, how to describe the rheological behavior of polymers, because we have to deal with 10 to the 18 chains at the same time. And no apparatus, mathematical and theory from physics can handle that. So the many-body tube model, for example, just have to throw away all the essential physics and end up not capturing the conceptual essence of what happens in rheology, for example. Same in glassy state, same in solid state. It still involves all these many chains, how they collectively form a network to deliver ductility instead of avoiding, therefore avoiding this failure of the chain network is the point. And we don't see easily a simulation can be done to prove it. And I'm here almost hand waving, but it's completely satisfactory to me because let me show you a few things. For example, if you add a little plasticizer to your polystyrene, any conventional understanding, the list of the 4, would say, oh, that should give you more ductility, okay? Because you're lower the TG. There's more mobility. We show with the 4% of this plasticizer, a ductile styrene turns brittle. We understand it. Well, brother, my theory can accommodate behavior like this. I don't predict per se. I don't claim I can predict, but it accommodates. Accommodate why? Because it can be interpreted as saying that the solvent really has lubricated the junctions where you overcome to achieve pull out. So you can cause the network to become weaker as a result of this lubrication. This is circumstantial evidence. If you have a brittle PMMA, if you cross-link it to an optimal level, it turns ductile. So this is actually a recent paper published this year. Okay, so preventing the pull-out through cross-linking currently work. There's more crazy things. This again published just now that usually based on conventional understanding, if you draw your polymer faster, you tend to encounter brittle response where you have ductility at the lower rate. At a higher rate, it turns brittle. Now we see the reversal. If you have certain rate that's ductile, if you lower the rate, it turns brittle. Same with temperature. Temperature usually, by definition, as I reviewed for you, as you move to higher temperature, you tend to achieve ductility from brittle to ductile. But we found if you further increase temperature, this ductile polymer can turn brittle. No way any conventional classical understanding could rationalize, make sense out of this. But read this paper. It's explained why this can be done. Why this can happen. I'm going to probably skip this. Basically, you can introduce anisotropy through squeezing in the melt state and explore this different effect of anisotropic networks. So, for example, when you have non-anisotropy, when you press a piece of material, the material no longer spread isotropically, so it becomes elongated. In any case, that's just so. In any case, this is my slides about implications. It really summarizes all the known practice that we have today. In particular, I think it takes my theory to properly understand the effect of bioaxial stretching. So, this three product is industrially widely known. The reason they do it is to alter the structure in favor of achieving ductility. And of course, it even talks about, we can also understand why typically immiscible blends suffer weakness because of incompatibility disrupt the network. Okay, lastly, let me use the next 10 minutes or less to talk about the part that we are mostly recently working on. So with this understanding of ductility, we were able to explain this famous Vincent plot, where he plotted the stress at brittle ductile transition for different polymers, basically about a dozen polymers. And this is my theory. And you can express my theory in a way that describes the fiber limit. I mentioned that people are really clever to make polymer fibers. The reason fibers is a clever product is they make all the chains aligned in the load-bearing direction, so that all the chemical covalent bond is bearing the load. Unless you break the chains, you will not have failure. So at least in that idealized limit, indeed you can achieve strength as high as 20 gigapascals. So it's easy to compute and find out. So that's the fiber limit. But generally, your polymer, the ones we see every day, is generally still in a coil form. They're not in the fiber limit, and which means this chain falls back and forth many times, wasting that cross-sectional area without bearing load. They only bear load once. So through that concept, you can understand that, basically, what we see is a strength that's 2 orders of magnitude lower than the fiber limit. Due to what? Due to these two factors. So why it's so weak? Due to these two factors. First of all, it's not in the fiber straightened chain limit. Secondly, the chains pull out instead of breaking. So each of this factor will introduce a factor of 10. And that's why what you observe is only a much lower strength, as you see here. This has certain implications. This means, if this is true, this means what you have is what you have. In other words, the 100 megapascals is all you have. Why this is so weak? Because it's coiled. But that's not how the textbook tells us. Okay? If you open the textbook, they will say, oh, it's weaker because there are flaws in the system. Okay? So this is all over the place talking about that. And there are people who even think that the brittle ductile transition I just explained require you to use fracture mechanics to explain. That's a total misunderstanding of the situation. So in any case, I don't plan to go through the entire fracture mechanics, but although you shouldn't be scared about this topic, because I have basically clarified the foundations of fracture mechanics in the way I could do through the papers and the talks in the YouTube. You can go there, but not for today. Today, I'm just trying to briefly say fracture mechanics is a topic about how presence of flaws, such as a hole here, lower the nominal strength. that you see. That's the essence of fracture mechanics. Okay. And there are different approaches to describing the condition for fracture mechanics. One is known, what I today call it energy perspective. But on the other side, the whole physics of understanding fracture is to understand what happens at the crack tip. And there's some misleading information saying that the crack tip has diverging stress. And this gave us a lot of headache. And people basically were busy trying to remove that headache. And my short answer to that question is, for our polymers, the crack tip is often blunted enough that there's no stress singularity to worry about. And that changes the game, which I don't have time to explain here. But basically, there were two ways to think about it. Today, I call this, our way of thinking about it is different than the so-called engineering perspective. This engineering perspective of fracture mechanics, as I learned it, is very frustrating because it doesn't tell you what molecular parameters determine the degree to which your polymer resists fracture. And because of the constraint that we are thinking in this energy perspective proposed initially by Griffith, we end up understanding the fracture in a totally different way when it comes to the so-called toughness of the polymer. And they find this toughness is much greater than surface energy. And therefore, this energy perspective forces us to say that this is all about so-called viscoelastic dissipation, okay, which we are developing our understanding to confront. So here's our perspective, and it comes very naturally from what we have done for the ductility of polymers. We basically want to answer this question. At fracture with a crack, what is the stress at the tip? Because if I know that, I can compare with my nominal strength. And if they are comparable, then I can claim that there's no flaw that play any role. So we naively started this way by developing a birefringence technique to look at the tip and see if we can explain why the observed stress is much lower than the fiber limit strength by a factor of 100. Our finding, save some time. Well, they are comparable. Okay? They are comparable, implying that your inherent strength is what you observe. You get what you get. And this is some detail showing you exactly that. So we take a PMMA, we make a notch, and then we stretch it until it breaks. By the time it's about to break, we can determine the stress level. In fact, we can determine the stress levels at any time during the stretching. So this is a plot of stress as a function of how close you are going to the tip. R goes to infinity to the right, minus 1/2 is when you approach the tip. So we find that we can resolve the tip stress, we can read the stress, and we find that stress to be comparable with a unnotched PMMA. So that changes the game. These are 3 papers talking about plastic fracture. We have another dozen papers talk about fracture of elastomers. Since this is more of a talk devoted to plastics, I will omit any discussion on the elastomeric fracture, which is absolutely a fascinating topic. So in any case, we have learned something previously not available. The resistance to fracture previously is characterized in terms of this toughness. It's operational. You can go ahead, make a cut, you can find the critical stress, you get Griffith's scaling law, you can find a number, but it doesn't tell you what determines this number. Therefore, it couldn't tell me how I design my material to have a larger number. So it turns out through this exercise of looking stress at the tip, we found that there is equivalently a way that, or rather equivalent, there is a way to understand what determines magnitude. It's determined by the strength it has and how blunt the crack tip is. So we are no longer blindly following a operational way of looking at this. And now we can really start to see how we can improve polymer. But ultimately, so these are just a few examples of different polymers. It's similar. This is PN. This is a PLA. So they all confirm the same thing. So ultimately, it's all about how to make polymer ductile so you can avoid this, so that the resistance to fracture can be greatly amplified. So I'm quick on this fracture part, but as I advertised to you, there is a collection of talks I have on fracture in my YouTube channel, where you can learn all the details. Most of them are from, in fact, all of them here are from presentations at recent meetings. And so here comes the implications. Is no wonder when you produce your polymers, you don't need to have a clean room to do it, because the dusks are typically too small to really lower your strength. Okay? And ultimately, you want to have ductility. That's the only way to improve toughness. And in other words, as you improve toughness, you end up moving a ductile polymer into, brittle polymer into a ductile polymer through the structural change, as I mentioned here. So, so I'm just listing a few points about the implications of our understanding of fracture. And I come back to this this chain, and this is how each of the parts is relevant. About rheology, we learned we need to change structure through fast enough deformation, called a fine deformation, so you can preserve the structural change, and that structural change during processing could lead to much better properties. So that's the backward way and forward way of looking at this. So in summary, these are the three questions. We know how to answer them. You need a high molecular weight. I didn't say too much about crystallization. You need fast crystallization so that you don't disrupt the existing chain network in the molten state. Okay. And secondly, favorable structures come from fast enough shape change, so you can manipulate the structure and effectively. And lastly, what happens is the material is have its strength because the chain networking makes cracks very blunt, so it can tolerate a lot of flaws of small sizes. So as I said, I have a channel. There are talks on fractures. There are talks on, or in fact, this whole courses on rheology, and there are talks on ductility. If I'm too brief, you can find them there. And this is my conclusion sections. You can see I mean, it's a very brief talk. It's not a very detailed one, but you can see the effort we have here was to, at the conceptual level, establish this full chain from processing to structural topologies. Yeah. So with that, I'm done.
Thank you very much for that, Dr. Wang. That was a great talk. Any questions from the group there? Just as a reminder that this will be recorded, and you should get the recording sometime late this week or early next week in your email that you registered through. So we do have one question here. Many companies, including mine, are increasing recycled content in polymers. How does recycled content impact the network concepts that you've discussed here?
Yeah, so that's exactly okay. Sorry, that's really where it fits all the in. I did make one comment about it that the issue about recycling. So let's say, let's not kid ourselves. First of all, we do recycling because we haven't found something that is better than polyethylene and polypropylene and cheaply make it, right? That's why we're doing the processing and recycling. And in this recycling, biggest problem is sorting. I have my colleagues working on that in terms of how you compatibilize the incompatible parts of your collected plastics. And if you don't have enough compatibility, you see you have a phase A that build a network because it has high enough molecular weight. You have a B that does so, but at the interface, I mean, it's completely trivial message for anyone, including the folks who asked this question. But there's nothing at the interface. If you have a compatibilizer, naturally, even that compatibilizer necessarily will have to be high enough molecular weight they can reach and untangle in my language of forming loops, uncrossability, to preserve the continuity of the network, in absence of which you're not going to have good properties. And then, of course, often through this processing, you can have degradation, you could have reduced molecular weight, you could have changed the crystallization rates. This all affects what you end up having.
Great, thank you for that. Someone else asked, could you briefly explain how crystallization kinetics can affect ductility?
Oh, yeah. So it's, as I said, it's not only in my, I'm teasing you all the time. And RCA under my name, there will be don't have to wait for this book under my name or chapter 7. There are two extremely lengthy back-to-back paper in polymer where we talked about it all. But in brief, half a minute is okay. This is why I started in this unconventional way for you guys. Is what you as I showed you that your polyethylene. Your polyethylene, when it's crystallized enough, it's brittle now, right? That's Mendelkern's work. Why? If you give enough time, which is the bad thing, so you want fast crystallization. But if it's slow crystallization, the chance have time to attach into the crystalline phase. In doing so, they completely rearrange the network. The network does not have enough of this uncrossability anymore, because the crystalline phase cannot tolerate it, right? So fast crystallization is the magic. Polyethylene works, even polypropylene works because they crystallize sufficiently fast. So that the network is preserved.
Great, thank you. There's another question here that started by thanking you for the presentation, and they said 2 questions. For the PLA you mentioned, can we still have the inherent shape memory behavior in it? And then the second question, which is kind of broader, is are the mechanisms for higher ductility in plastics at higher strain and high temperatures the same as the mechanisms of higher modulus and strain at break for rubbers when the temperature is sufficiently above TG? So maybe we'll take them too. Let's start with the first one. For the PLA, can we still have the inherent shape memory behavior in it?
Well, as far as I know about shape memory, it's really all about embedded stress in glassy state that gets released above TG, right? So because the shape change occurred in the molten state, you fix that shape change by trapping in glassy state. Once you go toward TG, it will start to remember, oh, I want to be back to my coil state. So there's nothing funny about, yeah, so that cup, I showed you, if you move, if you go above TG, not TG, in this case, in this PLA case, depending on whether you have crystallization or not. If you have crystallization, you have to go above TM, right? By that time, you may start to burn your polymer as well. But generally, if you go to a solid, generally, a glassy polymer has memory effect. It's because in glassy state you can trap that shape change, preventing it from return to its original shape, right? So as you move above to the liquid state, whatever residual stress will have the tendency of driving it backward, right? So I guess that's what you call shape change, because I don't, shape memory material has to play the role of valve versus below TG issue, right? So I don't see any magic in that topic in that sense.
Okay.
The
second question there was, was the mechanism of higher ductility in plastics at high strain and temperatures the same as the mechanism in elastomers or rubbery materials when you've got a higher modulus and higher strain at break when you're above the TG?
Oh, in fact, okay. So let's recognize the problem. It's quite trivial to say the following, that I sometimes tease my student that way. in plastics, all of it, crystalline or amorphous, the so-called yield point of brittle failure just involve a few % of shape change because it's in glassy state or it's in that crystalline state. Whereas for your elastomers, while above TG, it can be very stretchable and still undergo so-called brittle failure because the force is still building when it breaks. But that could involve several 100% of stress. So when it comes to the effect of temperature on elastomers, since you mentioned it, the elastomer is known to be weaker at higher temperatures. So actually they stretch less before rupture occurs in elastomers. In the case of polymers, as I have spent most of my time on, it's a matter of if you started with a brittle material, it's a matter of whether increasing temperature allows you to cross the brittle duct transition and turns ductile or not. And as you can generally agree, a ductile polymer typically is much more strain tolerant. Okay. But still, it doesn't mean it can stretch as much as a rubber does. Well, a lot of rubber cannot stretch very much. It depends on how much you cross-link it. So, so of course we have we are sitting in the whole picture because I skipped all the elastomeric part, but the temperature effect is understood in both cases.
Okay. Let's see, we've got a couple minutes left. I have one announcement I want to make at the end. So actually, I'm going to make my announcement and then I'll then I'll come back to the question. I want to keep you. So first, I want to say thank you to Dr. Wang for the excellent presentation and the discussion that he's had today, and thank all of you for attending on behalf of SB EPSTIV. We really appreciate your participation here in the EPSTIV event. We're going to be hopefully doing this moving forward, so please keep on the lookout from SB's EPSTIV. And we're always looking for volunteers for the board as well. So if you're interested in either volunteering with the board to help run the organization, or if you're interested in kind of further seminars like this, either you giving them or just receiving notification that they're happening, please let us know. You can respond to, I think we'll have some emails in the email you get with the recording if you'd like to contact us to reach out. But in the last kind of 2 minutes here, we have a question from somebody here says, can you briefly explain how crystallization kinetics can affect ductility?
Crystallization kinetics, yeah. Okay. There's a little switch of gears. So my talk was on glassy polymers. Now switch to a semi-crystalline polymer. What happened? There are two parts to it. If you have a semi-crystalline polymer, you can speak about so-called drawability or ductility, whichever we wish, either above its TG or below its TG. So as I showed you in the beginning, even above TG, this example, even above TG, polyethylene's TG is very low, you can lose ductility because you disrupted the network. So now it comes to the essential point, which you may learn better from the two papers I mentioned. A semi-crystalline polymer, you draw it, you lengthen it. By definition, it also needs to develop the ability to contract transversely. Otherwise, you cannot draw, right? Something will happen. Call it cavitation, call it stress whitening, whatever word you have. And so the key is that you need also a chain network that can properly melt or bring down the crystalline phase in conformation with the demanded shape change. So this is the role of the network. It needs it to pull chains out of the crystalline phase, make the crystalline phase mechanically melt such that the shape change can take place. So this is the part, of course, I skipped entirely.
Got it. Well, we're just about to hit time. There is a question here from somebody from Bailey, but I'll make sure Dr. Wang gets that, and they can send he can send you an email if there's follow up. But thank you all very much for attending. Have a look out next week for both the recording, some email if you're interested in being involved with EPSTIV, as well as there will be a survey in that email that we'd love for you to take to give us some feedback on this. Thank you very much again, Dr. Wang. Great presentation, very thoughtful.
Thank you. See you guys.